we're going to learn about Ampere's Law a little and about the Biot-Savart Law a lot more. Why Ampere's Law a little? Well, we talked about it in class yesterday. And what we're going to do calculus-wise for Ampere's Law is no different than what we're going to do algebraically with Ampere's Law. Just like with Gauss's Law, we pretty much use the symmetry for the calculations. So I'm going to go pretty quickly through Ampere's Law here. Just a little history. It was in 1826 when this gentleman, André-Marie Ampere, question? Oh, look at that. This gentleman that you can't see, André-Marie Ampere, developed his famous law. It's a lot like Gauss's law, except for instead of the flux through a surface being proportional to the charge enclosed, it's what he called the circulation, the magnetic field parallel to the piece of an imaginary loop integrated along the entire imaginary loop until it rejoins itself, was equal to a constant, that permeability of free space, multiplied by the current that's enclosed. Now we can see the equation. Thank you for actually raising your hand and letting me know instead of waiting a half hour and then saying, well, that was ridiculous. He never noticed. You see this here, double integral over the surface, right? Because it's a two-dimensional surface that is enclosed by a loop. And then J here, notice J is a vector. J is the current density dotted to dA, dotted to the little piece of the surface area. It has a direction. The current density has a direction. But to get current, you're doing this integral of J dot dA. And since J dot dA is going to give you a non-vector, that's why the current is technically not a vector. And so we're never going to do this part. I just have it shown so you can see, that's why we don't put a vector sign with the current. It's kind of silly, I think, because current clearly has a direction, but it technically doesn't. You had a question, Alex?
I'm just trying to figure out, so the DA is going along the wire?
Okay, you have a loop. So go over here. Let's say your loop is just a rectangle. And then you have your DA would be a little dx, dy. Now you notice I showed that as not a vector, right? The vector is going to have a direction with it, and the direction for the vector is always in the direction that's normal to the surface. So the direction of the vector I actually ordered the tip so I won't have all this skipping, is going in the direction out of the surface. So imagine that you're taking a wire now. Okay, so a wire, you have a current density in the wire. That is, you have charge flowing through the wire. And so in each little piece that's going through here, you can calculate, okay, this is how much charge is going through in this little piece, and this is how much is going through this little piece. And then you say, okay, now let's look at the cross-sectional area. So the wire is going like this. I'm looking at a cross-section. And I say, on this surface, I'm going to add up all of the charge that's going parallel to the area. And if I do that, then I'm going to get the actual current.
So those two areas need to be parallel.
That was only one area.
So that's the area you're talking about for current density?
Yes. I'm integrating the current density over the D area.
Oh, this is not for magnetic, this is for current density right now.
Yeah.
Okay. Yeah, I get it.
So the current density is not shown anywhere in this picture. The current density is this J vector. And so that's the current per unit area, current density, and then you integrate over the area to get the current.
So right now you're giving us a definition of what current
So yes, this here is the definition of current. And that's really the point of why I had it here. Okay. So applying it to a wire, well, we just did that in class yesterday, right? We applied it. We found the magnetic field at some random distance r away from an infinitely long wire. Why did we do it for an infinitely long wire?
It's confusing or gets really complicated if it's not infinitely long.
Yeah, if it's not infinitely long, it's going to be much harder to calculate, and it's going to be slightly different. So our calculation is technically only true for an infinitely long wire, but then we can wave our hands around a bit and say if your distance away from the wire is small compared to your distance from where you are to either end of the wire, then as far as you're concerned, that wire might as well be infinite. And so this is a good calculation for the current produced by a wire, as long as you are close to the wire compared to the distance to the ends of the wire. Right, so we do the calculation that's easy and that's relatively correct in anything that we're going to do. You know, if you're talking about the electric wires in your house, those wires are running for feet, and you only worry about this if you're within inches, so it's fine. Okay, then the next one we did in class again yesterday was for a solenoid. And remember, for the solenoid, even though it has a cylindrical symmetry, as Jeffrey pointed out, that cylindrical symmetry isn't really exploitable to us. Because if we did the circulation just based on the rules that you have to have closed loops for your magnetic field lines, you're going to have the magnetic field lines going something like shown here. The only option you would have would be if it's going left or right. And so if you make a loop that matches the symmetry, a circular loop around that, at all places, your magnetic field is going to be perpendicular to your ds. So you're going to get nothing for the circulation. So it's not a useful symmetry. Even though it has it, it's not useful. And so what we had was that rectangle that we made. That rectangle we made, and then we once again said, well, let's make it way out there so the magnetic field at the end is zero, so we don't have to worry about what's going on that end. And based on the symmetry, it's going to be perpendicular on the sides, which is a reasonably good approximation. Obviously, it's not a perfect approximation. And we were able to find the magnetic field inside the solenoid. So we've already done that. There's no need to do it again. And once again, that was based on an infinitely long solenoid. And then we recognize that as long as we are, near the center compared to the length, it's going to be an appropriately correct answer. Now we go to the new thing, the Biot-Savart Law. Obviously, these guys were French, hence it's not the Biot-Savart. Biot-Savart is my best pronunciation. I'm not a French speaker, so take it for what it's worth. So what's the Biot-Savart Law? The Biot-Savart Law is equivalent in usefulness to Coulomb's law. We use Coulomb's law to find electric field. A bunch of problems on that first homework assignment. The Biot-Savart law is what we're going to use if we don't have a nice, cool symmetry that Ampere's law makes easy to do. So what does the Biot-Savart law say? The Biot-Savart law says that if we have a wire with current going through it, we can calculate the magnetic field at some random point based on the current through that wire by integrating over each piece of the wire. So just like with Coulomb's law, we were finding the electric field that's created by each piece of charge. Now the Biot-Savart, we're finding the magnetic field created by each piece of current. So the actual law, it's written two different ways here. They're perfectly equivalent to each other. The difference is that R hat is equal to R vector divided by R. And so you have to the second power versus to the third power with the vector versus the hat. Sometimes you're happy having the vector on top, and sometimes you're happy having the hat on top. And so I just have it shown two ways. They're perfectly equivalent. There's no reason to show two ways except for to remind you that you could look at it either way. So what do we have? We have the mu naught over 4 pi, some constants. They're not throwaways, but they're just constants, times the current times ds, which is the little piece of length of wire that current's going through. So this is specific now for a wire, crossed with r hat, where r hat, we always have to know what r is. R is the vector that goes from the piece of wire to the location where we're finding the magnetic field. So R is not going from our point to the wire, it's going from the wire to the point. That was the same thing. Was it the same thing we had with Coulomb's law? I have to go back and think about that. But R hat, or R, is the vector pointing from the wire to the place where we're finding the magnetic field. So what's the best way to learn how this works? To do it, to use it. So we're going to use it for two different situations. Two different situations, both of which I gave you the answers in class yesterday. One of which we showed how it worked using Ampere's law. One where I simply said, this doesn't have a nice symmetry to use Ampere's law, so we have to find it a different way. This is the way we find it. So the first one I'm going to do is the one that we didn't work out in class yesterday using Ampere's law. Why? Because it's the easier of the two. That's why I'm doing it first. So we have a circle of current. How do you make that circle of current? I don't know. You put a little battery in a wire. Right? It is not important to me how you make it. You have current that's going in a loop. So here's a picture showing current going in a loop. And so based on the axes here, you see that this is the z-axis. So the loop is out toward me on this side and going away from me on that side. And I want to find the magnetic field produced by that current at this point P. So just like with Coulomb's law, the first thing I'm going to do is find what dB is. Now remember, dB is a vector. And so my picture already has things broken up, although I don't have the length of my vector arrows very well placed. So start with our equation and get the direction, because the direction we'll do separately from the magnitude. So for the direction, my direction is the direction of ds vector cross r vector. So I want the direction of that. So, okay, this is a real eeny, meeny, miny, mo. I've got a number behind my back. Choose a number between 1 and 10. Whoever's closer to the number I choose gets to use the right-hand rule. It was 2. So, Alex, right-hand rule for ds cross r.
Along that red line, right?
R is the red line. And ds is going to, well, it says here dl. Where it says dl, that's ds. D length.
So with dl kind of going out of the screen, r kind of going along the screen, then db would be going up like that. Okay, let's do it in a very very clear format. You take your right hand, and what direction do you put your index finger? In the first part of the component.
Which is?
Yes.
Yes. So your index finger is going to be coming out of the screen. So your index finger is going that direction. And then we need to orient our hand so I can make my middle finger point in the direction of R. What direction is R?
R is down and to the right.
Okay, so R is down and to, the right. So my index finger's there, my middle finger's down to the right, and my thumb points up and to the right, 90 degrees from the down to the right of R. So, of course, the picture already had it shown for us, but I want to make sure we can determine that. So I'm just going to make that bigger. So there's my dB vector. Now I need to break that into components, and I'm going to break them into components for a perfectly good reason. That wire is going in a circle, and this is along the line coming out of the center of the circle normal to the surface. That gives us the symmetry axis. We know that the amount that I have up in this picture is going to be exactly countered by the amount that I will have down if I choose this for my DL instead of this for my DL. And so the perpendicular parts, for every perpendicular part that's one direction, I'm going to have another one that's exactly opposite as I go around the circle. So I can just logically, by the symmetry, say, my perpendicular part, when I integrate it, is going to come to 0. It has to. If it doesn't, I made a big error. Now, we could go ahead and do it. I didn't do it in preparation for class because, well, there's not a lot of point in doing an answer that gets 0, except for as a check to make sure, yes, it gave me 0. So then I have the parallel part, or the parts that aren't going to add to 0. So our x-axis is defined, so that's the dBx. So I need to find the x component here. And so theta was defined in this picture. So let's use that definition for theta. There we go. And so based on that angle theta, how much of my dB is in the x direction? Okay, it's the adjacent one, so it's going to be times cosine theta. So now I need to find what the magnitude of dB is. Right, so dBx is dB cosine theta. Once I find the magnitude of dB, I can do my integral. So I have dB's magnitude is equal to mu naught I over 4 pi. And then I look and I say, what is the angle between ds and my r vector? It's 90 degrees, and it's going to stay 90 degrees because of the symmetry. And so that means ds cross r has ds cross r hat has a magnitude that's just ds. We've already taken care of the direction, so I'm just looking at the magnitude now. So the ds cross r hat, so I'm using the upper one, is just ds. And then I have over r squared. Now this looks good. Is it good? Is r a variable or is r constant? It's constant. Based on my symmetry, the r is going to be constant. So it really is good. The only variable there is the ds. So now I'm ready to do my calculation. And let's zoom out a little so I can see that and do my work. So I'm going to have b in the x direction is going to be integral of dB in the x direction, which is the integral from 0 to 2 pi r. That is the integral over the circumference of the wire, the length of the wire, of mu naught I over 4 pi r squared. And then I have cosine theta ds. Well, the only thing that's not a constant here is ds. And so we see what we can cancel here. Cancel the 2 pi with the 4 pi, and that leaves me a 2. From the integral from 0 to 2 pi r of ds. So the 2 pi r was the result of the integral. So the 2 pi and the 4 pi gave me 2 on bottom. The r canceled one of the r's. mu naught I over 2r cosine theta. Now, I usually like to take this, instead of putting it cosine theta, I want to calculate what theta is in terms of how far I am from the center of my circle. Whoops, I meant to come over here. So notice, using similar triangles, that there is the angle we called theta. And so that means that cosine theta is the radius of my circle divided by r, the distance away. I did put that correct, didn't I? Yeah. And then finally, using Pythagorean theorem, replace the hypotenuse r squared with the adjacent side squared plus the opposite side squared, because x is really the interesting variable. X is how far we are from the center of the circle to where point P is. So here I have an equation. Okay, there it is. For the magnetic field in the x direction on the axis coming out from the center of the circle. Now, this is a general equation for the circle, right? As long as you're on that axis. If you went off the axis, the problem would be much harder, wouldn't it? Right? We went with an easy problem here. We're starting out. What was the equation I gave you in class yesterday for a loop of current? It was for if you are at the center of the loop and you got
mu and I over 2.
Yeah, it's just mu I over 2r. So what we want to check is see if this actually gives us the equation I gave you and said, trust me, I'm a teacher yesterday. So what is different about this if I'm at the center of the circle? X equals 0. If x is equal to 0, I have mu I r over 2r squared. One of the r's cancel. Mu I over 2r. It's the same. So we've just extended that result to anywhere along that axis of symmetry. So that's a good application of the Biot-Savart law. We couldn't solve this in an easy fashion with Ampere's law. Now, anyone would say, but you could have solved it with Ampere's law. Well, yeah, you could have. Just would have been probably super hard. What we do is try to avoid the super hard in this class. I say it would be super hard because I don't know how I would do it. Now, one that we did with Ampere's law. An infinite wire, straight wire. Why is this harder than doing the circle? I am going to have to do a real integral, yeah. It's not a hard integral, it turns out, after you do all of your algebra. But the radius is changing, right? The direction is going to be constant, because if we do the direction, notice it has theta there shown as the angle between ds and r vectors. And if you use the right-hand rule, so now we'll go to Gila. If you use the right-hand rule, ds cross r, what are you going to get? So you take your index fingers and point up. And you need to bend your fingers down. There you go. And so your thumb is pointing into the screen, right? And note that if you're down at the bottom, your r is going to be pointing up and to the right. If you're up at the top of the wire, it's down and to the right, but it's always going to be on the same thing. So you're pointing the same direction with your thumb, regardless of which part of the wire you're looking at. So that means our direction here is simple. So I am simply going to say that my B vector is into the screen. That's what this is supposed to say. I told you that I order new tips, right? $10 for 3 tips. If I had the old pin, it's $1 for a dozen. Something like that. You know, it's not that the technology is any different, it's just a different size.
You should figure out how to make your own.
Yes.
That would only cost you $20 per tip.
We talked about cynicism yesterday. So once we've determined the direction, then we need to find the magnitude of dB. So find the magnitude. What's the magnitude of ds cross r hat? This is very straightforward. It's not hard like I tried to make it when I was doing it before class. Cross product is multiplying which parts? Perpendicular. So what we do is we just take ds times, what's the magnitude of r hat? 1. So we just drop that off, times sine of the angle between the two, which is defined here as theta. So that part was easy, but theta is going to change. Theta is a variable. And so if we put that into our dB magnitude, okay, that stuff's constant. Everything in green is changing. So we've got ourselves a little work to do, because how many variables do we have? How many do we want to have if we're going to do a single integral? 1. So we're going to have to convert variables. Now we've done something like this and we're going to use the same conversion. We did something like this when we used Coulomb's law on the infinite wire, or the semi-infinite wire. We could do this for an infinite or semi-infinite wire just the same. So here we can find the magnetic field due to just a piece of wire instead of for an infinitely long wire. So what was the substitution we used? I've given you a start. We used that angle. I had to name alpha because we called it theta before. Go ahead.
Because I remember we had to use a tangent.
Yes. One equation we used was tangent of alpha is equal to S over capital R. And then we took the derivative of both sides. The derivative of tangent alpha is d alpha over cosine squared of alpha is equal to ds over r. That was one of the two. Good job. That was the harder of the two. Alex, go for the easier of the two.
That was a long time ago.
We use cosine of alpha. What's cosine of alpha going to equal for this triangle? Capital R over lowercase r. And so how are these going to help us? Well, notice in my equation here, I have ds over r squared. So I'm going to take the one with the ds in it and solve it for ds. So this gives me So that's my ds. And then I'm going to use the other one to solve for, well, that had 1 over r squared, right? So I'm going to solve for 1 over r. So 1 over r is cosine alpha over r. Now, if I combine those, put them in here, so for ds, it's d alpha r over cosine squared alpha. And then for 1 over r squared, it's going to be cosine squared alpha, because it's squared, I had to square everything, over r squared. And then I'm going to be left with my sine theta that I still had, that I didn't substitute. What simplification can I make now? Cosine squared alphas cancel out. Good, I don't need to use that. And one of my r's cancels. Not both, but one. One last substitution. What's that one last substitution? I wrote down here the mathematical relationship. Yeah. With this tip, it actually takes an act of God to get a rectangle to form. That alpha is equal to theta minus 90 degrees. I know there's a 4 pi inside that box. I see if I can actually move this so there's not a 4 pi inside my box. It's easier to do this. Okay, so there's my relationship between alpha and theta. So what is d alpha equal to? D theta minus 0, because 90 degrees is a constant. So d alpha is d theta. So I can just put sine theta d theta. Well, now this has become an easy integral, because now I can say, my magnetic field is equal to the integral from theta initial to theta final. Actually, let's move the constants outside the integral sign. Mu naught I over 4 pi r. What's the integral of sine theta d theta? It's minus cosine theta. I swear I said the wrong thing, but it's minus cosine theta. Okay. So we have that, or if you prefer, okay, so notice I changed the order and put the minus sign in with my parentheses, so I just have less minus signs overall. So there's my equation for the magnetic field created by a current going through a wire. And it's all beautiful and perfect. I can leave it right there. But I do want to check it to see what I would have for an infinite wire. For an infinite wire, looking at our definition of theta here, if it's infinite, you're going to start with infinitely down below. Theta is going to be 0 for your initial angle. And then if you go infinitely up above, theta is going to be 180 degrees or pi radians. So we're going from 0 to pi. So for an infinite wire, cosine of 0 is 1. And cosine of pi is -1. So I'm going to have in parentheses 1 minus the -1 or 2. So that's going to give me magnetic field for that infinite wire is mu-naught I times 2. Oh, come on. Take the pin out, rotate it, put it back in. Mu-naught I 2, that really helped, over 4 pi r, which is equal to mu-naught I over 2 pi r. My tips will not be here tomorrow, but they should be here by Friday's lecture, I hope. So, is that the same equation we had for an infinite wire from Ampere's law? Yes! Yay! So excited. My derivation worked. That's why I sat down and did it while you were in chapel, so I wouldn't make a mistake. So, what have we seen here? We've seen that Ampere's law, or not Ampere's law, that the Biot-Savart law can be used to find the magnetic field produced by, of course, any random current going through any random wire. But we've done it for 2 simple cases. So when it comes test time, things that we will have, because I think we're getting close to test time again, aren't we? No, we can't be. It's only been a week since the test.
Yeah, we just got done.
Yeah, 1 week ago.
One thing.
Well, we have 2 things that you can have. You have Ampere's law and the Biot-Savart law. We will have an additional thing. We will have Maxwell's equations. That will be our final piece for the calculus things we can have. Yes?
What happened to the negative from the cosine?
Okay, what happened to the negative was I included it. This minus sign here was moved in here, so instead of having final minus initial, I have initial minus final.
Oh, okay.
Right, because it's an important thing, and you see me make enough minus sign mistakes to know I could have made a mistake. Other questions? Yeah.
I just kind of need a bigger rule for where theta initial and final came from. Like,
Okay, so here is our picture that defines theta. You see, I've got my box now through theta. Here, I erased the box now. So if we have an infinite wire, we're going to start way down here. And so it's essentially coming up with no angle, because you're infinitely down, no angle to get out to a finite distance. If you had a finite angle, you'd go out to an infinite distance. And so we're starting at theta initial equals 0 if it's an infinite wire. And if it's an infinite wire, it's going to go up to infinity. So theta final is going to be 180 degrees, because if it's anything less than 180 degrees, it's going to go out infinitely in the x direction. So that's where I got the limits that I applied. But the equation without the limits would apply for any length of wire. So this equation right here, I could have applied for a wire that basically, it could go from, I could be at the bottom of the wire going off to infinity, and I would just put in, from pi over 2 pi. And that would give me the magnetic field for the semi-infinite wire. Right, so the work that we did with a semi-infinite wire charge, we can do the exact analogy here for a semi-infinite wire of current. There are some bigger difficulties. How do you make a semi-infinite wire of current? Where's it start and end? Because current can't just be there like charge. But a kind of problem that I've done on tests is, this is what I did on last year's test. If you look at it, I had a problem where I had current going through something like this. And so, of course, you have the R1 and the R2, and you calculate what the magnetic field is right in the center. That's the center of the circles, if they were complete circles. And so, in that case, you have to think about how you approach it. Once you get how you approach it, it's not that hard. How would you approach that? First of all, which law are you likely to want to use? The Biot-Savart law or Ampere's law? The Biot-Savart, because you clearly don't have an exploitable symmetry here. So we're going to use the Biot-Savart. And what was the first thing I did in both of the example problems? I evaluated the direction. So now we have to worry about the direction for three different pieces: the big arc, the small arc, and the two sides. Well, if you do the two sides, you see that your current is parallel, so your DL or DS is parallel to R. So what is DS cross R if you're parallel? 0. So boom, those two don't contribute. Now you have just two semicircles. And so for the semicircle, you do the work that we did, except now you don't have the bottom half, so you're not going to have adding up to 0 in the perpendicular direction. And so you're going to have to do both the x direction and the y direction for the half circles. So it does have an additional sophistication there that you have to do both the x and y direction, then you have to, right? And then you have to integrate both of them. Okay, I am done. Are you guys done? All right. I'll see you for another lecture in 1 hour and 45 minutes. Woohoo, extra long.